Hi, we're Group 33 and we're presenting our work about detecting neurodegenerative disorders from speech. So, the description of the problem is as follows. Such diseases like ALS cause speech changes before clinical symptoms become even obvious, and current diagnosis is subjective and slow. However, speech comes in handy because it's a non invasive, low cost and information rich signal, and it can enable earlier detection and eventually reduced burden on clinicians. Our novelty is that we came up with our own architecture for ALS classification, which was different from prior work that uses a vision transformer for classification. Our task is as follows. It's a novel approach to ALS detection, and the architecture is as follows. We use data augmentation, then we use wave-to-vec embeddings, and then we process that by a feature extractor, followed by an MLP classifier at the end. And then we do ablation studies to get the best parameters. The data set is as follows. We have 339 speakers, and 134 of them are healthy controls, while the rest are ALS patients. We use vowels and repetitions, and we have 5 classes ranging from severe to healthy controls. Data augmentation was also used because we did Gaussian noise, volume gain, and speech change as shown here in the specifics. And we also do some pre-processing from resampling to normalization and padding. There was no explicit MCCC or spectrogram conversion because wave-to-vec takes raw audio. And this is a analysis of the data set. Here we have the class distribution. Here we have the count of the classes by sex, and here we have the count by age.
Okay, so now let's move on to our approach. For our model architecture, we have three main parts: the feature extraction, feature aggregation, and classification. The feature extraction component operates on each of the 8 recordings of a given subject in parallel. The first part of this component includes a wave-to-vec model that computes downsampled feature embeddings for the temporal dimension of the recording. Then the second part is a post-processor which uses an attention mechanism to reduce the feature embeddings through a weighted sum into a single fixed size embedding per recording. And then we have the feature aggregation component, which averages each of the fixed size embeddings for the 8 recordings. And this is then sent to the final single layer classification multi-layer perceptron that predicts our output label. Now, the pre-trained wave-to-vec embeddings extractor is fine-tuned through low-rank adaptation, while the rest of the components are fully fine-tuned end-to-end with the cross-entropy loss training objective.
All right, on to our results and discussion. So our evaluation metric that we used was macro F1 score. This was as a result of our data set being highly imbalanced, and accuracy alone wouldn't reflect our real performance. Models could simply just predict the most common class and achieve reasonably high accuracy. And so we wanted to avoid this and show some real performance across all cases. So in our ablation study, going from our VIT baseline, which had MFCC spectrograms as our input features, we had a lower MACRF1 score, 0.44 roughly. But as you can see, when we improved to our wave-to-vec architecture with some extensions and our post-processing of our features, we achieved much better performance. The best being our attention-based post-processing. So looking at this one, best model in terms of its per class performance. You can see it achieved much more balanced performance across classes as compared to our earlier experiments, which either performed very well and over predicted on the rare cases, and some other ones under predicted them. Yep, this is a good balanced performance. In terms of our small supports from the small validation set, we also ran some studies across different random seeds to show that these improvements are real and not just a result of initialization, achieving a mean and mean very close to our peak performance and a small standard deviation. So to conclude, we developed a wave-to-vec based system for ALS and dysarthria detection. We achieved best performance of 0.824 at MACRF1 score. And we observed that pre-trained models and data augmentations really improved our results significantly, but class imbalances remain a bottleneck. In terms of future directions, we hope to explore other pre-trained encoders and synthetic data augmentation to improve performance. And a real-world impact is our speech. Speech offers a non-invasive biomarker for early neurodegenerative disease detection, and this has potential integration with clinical workflows for early intervention. These are our resources. Thank you.